Hi, today I'm going to talk about the background of the Warren Truss Bridge and our truss example, the 107th Street Bridge. So first, let's talk about the general history of the Warren Truss Bridge. Okay, so the first bridge of a truss design was built in the 1840s by Alfred Neville in France. This bridge used an isosceles triangle framework over the equilateral framework of the Warren Truss Bridge design we see later. In 1848, James Warren and Wilby patented the Warren Truss Bridge design made up of equilateral triangles. This design was soon used far and wide to build bridges all across Britain and India. Traditionally, the railway infrastructure mostly used this design, which was picked up by the US in the 20th century. Since then, the Warren design has gained immense popularity, causing these bridges to pop up all over the world. The Warren Truss design uses equilateral triangles in the framework to spread out the load and limit the force of compression and tension in the individual bridge parts. Overall, this is done by building the bridge out of stringers, floor beams, bracings, cords, struts, and of course, the deck, as shown in Figure 1. There are many advantages to the Warren Truss design. For example, ridged triangles make it very strong. The bridge only requires a small amount of building material, and it can be constructed through individual pieces, allowing diversity of patterns as well as improved cost effectiveness. However, this design is not without problems. The joints and fittings of the bridge need to be checked constantly, causing maintenance to be quite expensive. Furthermore, if the bridge is not designed properly, lots of material does not contribute to the bridge and can be seen as a waste. All right, now let's talk about our truss example, the 107th Street Bridge. The Warren Pony Truss Bridge over Coon Creek on 107th Street in Iowa is a very old truss bridge residing in the beautiful green countryside of Iowa County, as can be seen in these images here. All right, the dimensions vary with deck width of 15.7 feet, a total length of 62 feet, and the length of the span at 60 feet. Additionally, the height was found to be 13.48 feet or 4.11 meters, which we will later use in our calculations. All right, now some historical facts. So according to Bridge Hunter, this Warren Pony Truss Bridge was built in 1920 by an iron and steel manufacturer, Jones and Lawland Steel Company of Pittsford, Pennsylvania. Later, in 1962, the bridge was rehabilitated and is still open to traffic today. Although the bridge is old and rusting, according to historicbridges.org, its national and local scale for historic significance ranks at a 5 out of 10 due to the beauty, heritage, and craftsmanship endowed by it. Thank you for listening. Here's my works cited.
Hello, I will be going over the rigid body equilibrium for our Warren Truss Bridge. In order to start this problem, we first had to make a few assumptions. First off, we assumed that at joint A, it was supported by a pin. This leads to a horizontal and a vertical reaction force. Additionally, at joint I, we assumed that there was a roller. This leads to only a vertical component of the reaction force. Notice how this system is statically determinate. Another assumption we made is that there was a 5 kilonewton asymmetrical load applied at joint D. This can represent a car or anything going over the bridge. Another assumption we made is that these vertical members, starting at joint C, E, and G, are all zero force members. This Warren Truss Bridge is made out of equilateral triangles, which gives us our angle of 60 degrees here, and then we can use that to solve for the height. Once we have all of this in our free body diagram, we can then sum our equilibrium equations. We started with the forces in x, which gives us a sub x equals 0 kilonewtons. We then summed our forces in y, which didn't lead us anywhere, so we then had to sum moments around a to eliminate a sub x and a sub y. That led us to find I sub y, and then we can get that a sub y using the sum of the forces in y. All three of these reaction forces are going to be the same regardless of which method is used to solve for the internal forces in the members of this bridge. Method of sections and method of joints will all use these three reaction forces to sum the forces in all the members.
Hi, welcome to the method of joints part of the calculation analysis. So after our assumptions that we made previously and calculating the reaction forces, we can start by picking a joint, and it's best to pick a simple joint like joint A. First step is to draw the free body diagram, including the reaction forces. We know A of x is 0, and then A of y we calculated before was 3.125 kilonewtons. So now first you can assume the directions of the forces, the two force members you don't know, like AB and AC. But sometimes it's obvious, like the way they have to go. Like AB has to go down to cancel out the AY. If it went up, then you'd have nothing to have the sum of forces in the Y direction be 0. So first you should start with the sum of forces in the Y, because there's only one unknown, because we have the reaction force. If you did this the sum in the X direction, you'd have two unknowns. You'd have the unknown AB and AC. So doing Y first works out because we already know AY. So all we need to find is AB. And after finding that, then you can do the sum of forces in the X direction, because now you know AB, all you don't know is AC. So it's just a simple one equation, one unknown. At first, we assumed it was in compression, and we were correct because the answer was positive. If it had been negative, then we would know it was going the other way. And it's in compression because the reaction force of it is pushing towards the joint, meaning the force inside the two force member would be pushing away from the joint, meaning it's in compression. And then the opposite is true for AC. Because AC is pointing away from the joint, then inside the two force member, it's pointing towards the joints, meaning it's in tension. And so point B is the same thing. You draw a free body diagram, you assume directions. You already know AB is in compression, so you assume the same for point B. It has to be the same. And then you start again with the Y, because you already know AB, but you don't know BC. So you calculate BC, and then you do sum of forces in the X direction, because there's two, now there's only one unknown. So you calculate that. It's all simple one equation, one unknown. And you go through doing the same thing for every joint. Joint C, joint D. Joint D is a little more complicated because there's 5. You start with sum of forces in the Y. You know the 5 kilonewtons is coming down, and you already calculated the force in CD up in joint C, right here, CD. So then all you'd find in that would be DE, and then sum of forces in the X direction. You already calculated BD up when you did joint B, and you already know CD and ED. So all you'd have left would be force DF, and the same would be said for E and F and G. And then once you hit H, you only need one joint left to calculate. You've already calculated the rest. Sum of forces in the Y. Once you find HI, then using the sum of forces in the Y, you can check your answer by summing the forces in the X, and you have to get 0. And here we got 2.163 minus 2.166. So it's not exactly 0, but it's 0.003. So that's just rounding. And then joint I isn't necessary at all, because we already have every other force in all the two force members. But just to check, make sure the answers are correct, we can sum the forces in the Y, and we should get 0 with all of our numbers we already know, and exactly 0. So that works out. And same for the sum of forces in the X direction. They're all 0. So it works out. That's all you do for method of joints. You go joint by joint, showing all the forces, assuming forces. If you get negative answers, then you flip it and you know it's in the other direction. And if it's pointing towards the joint, then the beam is in compression. If it's pointing away from the joint, the beam is in tension. And that's it. Thank you.
Welcome to this sections part of this video. As you can see, we have a small diagram of the bridge set up, and then there are numbered cuts that we're going to make through the bridge because we are going to do method of sections. It should be noted that any of these cuts can be performed in any order. That doesn't really matter. All that matters is that you do the whole bridge as a free body beforehand so that you can work out the external forces. And Caden went over how to do that. So as we go down, we're going to start with this first cut because that's how I labeled it. You make your cuts, and for each beam that you cut through, you replace the beam with a vector. And I assumed that all of these were in tension. That way I know that if I get a negative number, it's in compression. It makes everything very simple. As you can tell, the beams that we don't cut through, we just leave as lines because we're not looking at the internal forces in that beam. And since it's a two force member, they cancel out. So looking at all of this, you get 3 equations, force in Y, force in X, and then you do a moment equation. I recommend doing the moment equation on the joint that has 2 unknowns. That way you'll actually be able to solve it. And from the force in Y, you can immediately solve for BC. It's a positive, so it's in tension. Force in X, you can't immediately solve. So you go to the moment about B, which immediately allows you to solve for AC. Go back to the X direction, gets you BD, and you've discovered the forces in those three beams. If you want to check yourself, you can do it on a different cut, cutting through the same beam and then some different ones. And here we have that member BD again, and we did get the same number. So it's a good way to check yourself on a test. Here is the free body for the second part and the answers for the second part. If you want to pause it. And then here is the free body for the third part and the equations for the third part. And the free body for the fourth part and the equations for the fourth part. Hope this helps out. And these are just the T's and C's are for tension and compression.
Hi, let's briefly recap our answers that we calculated for our members. So as you can see, this is the method of joints, and basically I'm just going to scroll through and just show all the answers once more and then compare it to the answers that we calculated on this truss analysis software. All right, so as you can see, the members go from AB all the way to HI here, and then when we put in our dimensions and calculate and make our Warren Truss Bridge through this software and hit submit, then we get these answers for our members, which if you compare them to whatever they match up with, like for instance, AB would be from 1 to 2 because of the points, and then from 1 to 2, so then this member is going to be member 1, and then you can find that our answers do in fact match. And that is a good sign because that means that we are correct when we calculated this. Thank you.